What are the four periodic table trends and how do they work? The first periodic table trend is electronegativity. Electronegativity is the measure of how badly an element wants to hog electrons. For example, an oxygen atom has 6 valence electrons. A hydrogen atom has 1. Hydrogen and oxygen bond so that the oxygen and hydrogen atoms both have full valence shells. The new molecule, H2O, now shares its electrons between hydrogen and oxygen. However, because hydrogen has a higher number of valence electrons originally, its ability to hog electrons is greater, therefore giving it a higher amount of electronegativity. As we move right on the periodic table, the number of valence electrons in each atom increases, therefore increasing electronegativity. As we move down on the periodic table, each atom has an increasingly larger number of shells separating the valence electrons from the nucleus, which increases the interference between them and makes it more likely that the valence electrons will be given away to another atom to create a full valence shell. This means that electronegativity decreases as we move down the periodic table. The second periodic table trend is atomic radius. Atomic radius is the measure of the distance between an atom's nucleus and its valence shell. Potassium has 19 protons, while krypton at the other end of the periodic table has 36. Both potassium and krypton have 4 electron shells, but potassium only has 1 valence electron, while krypton has a full 8. Because krypton has so many more electrons, it may seem that krypton has a bigger radius. However, this is not the case. Because krypton has a greater positive force pulling it in than potassium and has a fuller valence shell, its nucleus pulls the valence electrons towards the center, and the atom contracts to become smaller than potassium. Therefore, as we move right on the periodic table, the atomic radius becomes smaller. As we move down on the periodic table, the number of valence shells increase, making the atomic radius larger. The third periodic table trend is ionization energy. Ionization energy is the energy an atom needs to lose or give away an electron. For example, potassium has only 1 valence electron in its shell, so it would be happy to give it away to become more like argon, with a full valence shell of 8 electrons. This means it has a low ionization energy. Krypton, on the other hand, has a full valence shell of 8 electrons and does not want to give away anything since it's perfect as it is. This means that krypton has a high ionization energy since it needs a huge amount of energy to ionize it. Therefore, as we move right on the periodic table, ionization energy increases. As we move down on the periodic table, the number of shells between the positive nucleus and the valence shell increases, which shields the negative valence electrons from the positive force drawing them inward. This is called shielding effect. And it means that ionization energy decreases as we move down the table, since electrons don't have to work as hard to leave when they are shielded from the positive force drawing them in. The fourth periodic table trend is metallic properties. Metals are known for their malleability and their ability to conduct electricity. These properties both stem from the ability of certain atoms to share electrons. Elements with higher metallic properties, such as cesium, barium, and francium, have a low ionization energy that give them the ability to share electrons easily with other elements. Elements with less metallic properties, like oxygen, fluorine, sulfur, and chlorine, have very high ionization energy and are less likely to share electrons. Therefore, as we move right on the periodic table, metallic properties decrease. As we move down on the periodic table, metallic properties increase because a higher shielding effect decreases ionization energy and makes it more likely for a certain atom to share electrons. The most important thing to understand about the periodic table is nuclear charge. Due to the shielding effect, electrons in shells farther away from the nucleus experience less of a positive charge from the nucleus than electrons in shells closer to the nucleus. The nuclear charge is the charge of a valence electron fields with the shielding effect in play. As we move down the periodic table, the number of shells increases, which therefore increases the shielding effect. Because of this, the nuclear charge decreases as we move down. As we move across, the nuclear charge should increase a little since the positive charge from the nucleus is increasing while the shielding effect remains the same.